this is definitely additional material. So another way you can use the chi-squared test is what's called a goodness of fit test. They're not particularly common tests, though you might come across them. They might be more common than I think they are. So they're used when you're trying to find out if the distribution of data fits a particular model when your data is discrete. So because what you've got in a chi-squared test, what you've got is counts within each one of your different categories. So you can divide distribution into the bars of a histogram, so those effectively become your categories, and you can count how many are in each one of your categories, and then you can compare a theoretical model to what you actually observe. So the data has been used to look at outbreaks of war within a year. It could be the number of shirts sold in different sizes, could be the number of individuals kicked to death by horses in each year. These are things where people have used these kind of approaches. You can also use it to test ratios to see what percentage of people fall in each of the different categories. If you know something about diseases, you could compare them from different locations. So Westminster against London Met, what's the probability of students having chlamydia, for example? So you could transform the count data into a ratio as well if you wanted to do, and then you could use the binomial test. But if you've got more than two categories, then you have to use it as a chi-squared. So in this example, you're looking at leaf miners on the side of a holly tree. Now this is a particularly mean experiment that somebody has got a student to do. What you've got is a holly tree, you've divided it into three different proportions of height, so 0 to 2 meters, 2 to 4 meters, 4 to 6 meters, and what you're looking at is how many leaf miners are on the leaves. Now that's going to be a very painful experiment, finding all the leaves that have the marks of drilling on them at the different heights. Now just looking at the data, you see the observed numbers 131, 38 and 2. It's quite clear that there's no constant relationship at the different heights. They're very frequent at the bottom of the tree, not so frequent at the top. But this is also because I don't really think the trees are a cylinder. They have more leaves at the bottom because they tend to be wider. So it's not perhaps a great experiment. And it's definitely not a great model to assume that you're going to have an equal number at each of the different heights. But that's the basic first model that we're going to try. So we're going to do a chi-squared test to see if they fit those model. So the chi-squared test, the test statistic is chi-squared equals the sum of the observed minus the expected squared divided by the expected. The value of chi-squared is the test statistic, and we've seen this before in the standard chi-squared test for categories. You can then calculate the probability of having a test statistic of that particular magnitude. The bigger it is, the less likely it is to happen by chance, because observed minus expected is turning out to be a very big number. So if there's a big discrepancy between observed and expected, then your model is not true, and your hypothesis has to reject the null hypothesis that your model is true. There is a problem if you've got very small numbers, so you need to have expected values of any of the categories being larger than 5, because otherwise you'll end up with artificially large numbers when you divide by the expected on the bottom of that formula. You also need degrees of freedom, which will be the number of categories you've got minus 1. So the basic thing for the leaf miner data is to test if there's a relationship between the height on the tree, number of leaf miners. It's the classic goodness of fit test, and you can carry out these tests in SPSS. Now if you use SPSS to collect the raw data, then what you would have is a line for each one of the leaf miners telling you which one of the different heights you've recorded it in. But what you're more likely to get is a summary set of statistics. So you're likely to end up with a total for each of those different heights, like the summary table that I showed before. So here is the variable view for a data set. So it's got heights, which is height 1, which is 0 to 2 meters, 2, which is 2 to 4 meters, 3, which is 4 to 6 meters. And then you've got frequency. what you've got is labelled values for your different heights, and then you've got measures your frequencies. You've got 131, 38 and 2. Now, as I said, if you had the actual data, what you would have is 131 ones followed by 38 twos followed by 2 threes. Now you can get this effect by using what's called weighting of cases. So if you go to data menu in SPSS and you go to weight cases, you can then weight the cases which are height. That's the only variable you can do any kind of weighting for, the only categorical variable there. And you can weight it by frequency. So this means it will transform internally within SPSS to having 131 ones, 38 or whatever it is, twos and 2 threes. Once you've done that weighting, then you can go to Analyze Non-Parametric Tests. And this is an example of a test where you've only got a single sample. You're not comparing independent samples or related samples, there's just one sample. So you put in frequency. You put in height as your test field. Frequency is already being defined using the weighting, so it doesn't play any other role in this calculation. So height goes into the fields. Objective, as you've seen before, is completely automated. And you could go to settings, but again we want to leave it on automated. So you press run, and this gives you the output that says null hypothesis. The categories of height occur with equal probabilities. So one sample chi-squared test, the significance of this is 0. You reject the null hypothesis. There is no way at all that you've got an equal distribution of leaf minors across the 3 heights. The total value of n is 171. The test statistic is 155.474. It's got 2 degrees of freedom. P-value is 0. If you look at the bar chart for the goodness of fit, you've got the hypothetical ones and you've got reality, and you can see there's a big discrepancy in the bar charts. If you'd done this as a legacy set of tables, then you would see the 131, 38 and 2, the expected value is 57, 57, 57, so the difference observed minus expected is 74, minus 19, 55. Those end up squared and then divided by 57, and then those are added together to give you the 155.474. Now, that's a very silly model, having them all equally likely, so you can create a more complicated model. So this time, instead of just clicking on settings to do automatically choose the test based on the data and automatically create the hypothesis, what you can do is click on customize the test and compare observed probabilities to a hypothesized one as a chi-squared test, but this time you're going to specify the hypothesis. So when you click on that and you go to its options for the chi-squared test, you can have category 1, 2 and 3, and you can put in different relative frequencies. So before they were a third, a third, a third equally split. But now we're going to say in the lower limbs of the tree we want to have twice as much as the mid-range and then half again when you get to the top. So as the total needs to come up to a relative frequency of 1, I've put 0.6, 0.3 and 0.1, giving a total of 1. Now I can run the test again and see if this model is a better fit for the chi-squared test. So now the categories of height occur with the specified probabilities, not with equal probability. It's one sample chi-squared test. The sig value, the p-value, is still 0, and I still reject that hypothesis. So it's a better model, but it's still nowhere near modelling actual reality. I can tell it's a better model because if I look at the test statistic, it's now 24.643, because observed minus reality is a lot closer to one another. Degrees of freedom is 2, but there's still not evidence for that model. If I go to the bar charts, you can see that the height of the bar charts are much closer than they were before, but I'm still not completely capturing the differences in the numbers of leaf minors between the different heights.